here. The present topic is very useful for all the practicing engineers, particularly working in open cast mines. Assessing and monitoring of stroke stability is very important, and this activity should form part of the overall productivity and safety management strategy of the open cast mines. Successful slope design requires the gathering of information regarding the site geology and characteristics. So it is very pleasure for me to inform that eminent personalities, Dr. I. Sachana Garu, Director of Mine Safety, Northwest Zone, Ajmer Region 2, Udaipur, who did the PhD in slope stability from IIT, ISM Dhanbad, and Sri S. Vikram Garu, pursuing PhD as Senior Research Fellow, IIT ISM Dhanbad, and Sri SVSS Ramalingeshwar Garu, Retired General Manager, HRD from SCL, who is right now with me. So he'll be the moderator. And with this opening remarks, I request Sri Karuna Kumar Garu, Honorary Secretary, IEA Kothagudem Local Center, to introduce the panelists and the moderator and further proceedings. Thank you for giving me this opportunity.
Thank you, sir. Thank you. Sir, if I may go to further, sir?
Yeah, please. Karuna Kumar
Yes, now I am going. Yes, sir. Yes, sir. It is a privilege to introducing the panelist one. I'm happy to, first of all, I thanks to the Dr. I. Sachinarayan Garu, Director General of Mine Safety, Ajmer Region 2, Udaipur. Recently, he was promoted as a director. I congratulate him one, and also thanks for accepting this proposal webinar with our request. Thank you, sir. I briefly introducing his profile to all the audience of this webinar. Dr. Inumula Sachinarayan is presently working as the Director of Mine Safety at Director General of Mine Safety, Ajmer Region 2, NWZ, Udaipur. He also served in a different capacity in Singarain College Company Limited. He is expertised in mine safety and planning, mining methods, and stope stability. He graduated in mining engineering from Kakatiya University, Telangana State, acquired MTech in mining engineering from IIT Kharagpur, and PhD in slope stability from the IIT Indian School of Mines. He was expertised in different subjects, production and productivity, numerical method, statistical analysis, and use of continuous miner technology, etc. National and international general conferences. He has delivered more than 50 experts lectures in India. He is a recipient of the national award like a SRG IT Award 2021 and Dr. ML Janwar Award 2021 from Mining Engineers Association of India, and Best Idea Singareni Award. He also taught mining engineering at different engineering colleges, part-time lecture. He played a key role in the successful completion of the stopping panel under the Jalaram Wagu at GDK number 3 incline without disturbing it, which it was first of kind in the history of the Singarain College Company Limited. He was instrumental in achieving the record production of the 1,393 tons by LHD on 9/12/2005, created in the Singarain College Company Limited. He worked as a member of the board of the governors of the TechCube at University College of Engineering, Telangana. He played a key role in the building DGMS as a digital DGMS, implementation of the comprehensive end-to-end e-procurement to the GEM and CPP portals, geotagging of all DGMS offices in a Bhuvan portal, preparation of the documentary films, and organization of the National Safety Awards in Mines, and contributed to improving a safety in mines for the last 9 years. Sir, with this is a profile of the Dr. I. Sachinarayan Garu. I hand over into the panelist one. Please go through our today's topic. Thank you.
Thank you, Karuna Kumar sir.
I request to audience, please mute. The presentation is going on. I request to all the audience, please mute.
Am I audible to all of you?
Yes, sir.
Yes,
Yes,
sir,
sir.
it's audible and visible, sir.
Yeah.
Okay, okay. Thank you, thank you. Thank you, Kanukumar Saab and Janikram Saab and Ramalingeshwar Saab and other panelists like B. Srikant. First of all, I congratulate you because in remote area like Kottagudem area, the Institution of Engineers has made a local chapter there and conducting so many seminars. So I am very glad to know that, and I am also very much privileged to give a lecture on design and stability analysis of open field slopes in our this Kottagudem chapter. Thank you very much for giving this opportunity for the Kottagudem chapter. So as I said that our Janikram sir already told that in today's scenario there are so many slope failures, so many, and recently there are the Rajamahal incident is the very very high disaster that involved 23 fatalities, and it is in the Indian history. This is a major disaster which was occurred due to slope failure. So there is a need, very much need for design and stability analysis open pit slopes in coal mines, especially in coal mines, because they are going deeper and deeper. I will explain in detail by slide. So why, as you know, all of you know that it is open cast mining is a very cost-effective method. So most of the underground mines, if you see BCCL and ECL, even in Singapore also, underground mines they are not profitable and they are very hard conditions. Due to that, when most of the mines are underground mines are converting into open cast mines, because today if you see in India, 95% of coal production is coming from the open cast mines only, because of its various advantages like cost effective, high grade of mechanization, large production values, and even why we are going to this one, because with the new technologies and new improvements in the scientific studies and other technologies are coming. Remote LHDs are coming. Remote operations are going. Open cast also from the day from drilling to, even if you go to Australia, from drilling to and transport of the coal, total manless dumpers are there, manless trains are they are using it, and drilling all operations. So you can by sitting in the boardroom, you can operate all the excavators and the dumpers, drill machines, all those things. So these much technology advancements are there in Commerce. So we are going deeper and deeper. We can in future we can see at a depth of 600 meters, 700 meters also, because of these advanced technologies. As I told you, daylighting of the last making underground mines in open cast mines, increasing number of mines to meet the demand. Now there is a auctioning and privatization of the mines are there. Most of the private players coming into the picture to open the new mines. So increasing the risk of high wall slope failure. So because we are going deeper and deeper and we are expanding the mines, and most of the non-contractual outsourcing people are there. They do not know much regarding the safety and mining. They are entering into this field. There are the risk of high wall slope failures, and the conditions are worsening in respect of the safety and the stability of the pit slopes. So if you see the last 20 years, the accidents due to slope failure, 30% of the accidents in open pit mining are contributed. The only one and only main cause is the slope failure. So due to slope, if you see 1997 to 2017, if you see this is the ground instability in open cast mines, the fatalities occurred due to slope failure are around 30%. If you see if you go to the Disasters. There are 4 disasters in Indian mining, open pit mining history. All 4 disasters are caused due to slope failure only. So this is the grave concern, and we need to improve this thing. All these things in the 2019 also, this after the Rajmal incident, we made it this scientific study and monitoring of the slopes now become the part of registration. The DGMS made it a compulsory and mandatory. The owners of the mine management should do the scientific study and should evaluate the method of working and how to do the dumping, how much height the dump height should be, and what are the precautions they should be taken, what is the monitoring methodology, and what is the frequency of monitoring. All those things they should, with the consultation of the scientific agency, they need to develop one scientific study and need to submit it, and they have to run the mine according to that scientific study. So these are the some cases of the slope failures. Rajmal, open cast, in Singareni, if you take Dorli OCP1, Midpalli 1 bench failure is there, or Dorli OC1, there is a catastrophic failure, but luckily there are no fatalities in Dorli OCP1, and Junakunada also around 200 meter high wall fails at a time because of some indications. The management has taken proactive measures so that they evacuated all the people. So it avoided the major disaster in Junakuda Kalari. So what are the root causes of if you analyze this, we have taken for this analysis. I took around 100 slope failures, and from the 100 slope failures, what are the regions? If you analyze, then foremost one is the unscientific design and poor monitoring. In olden days, there is a thumb rule that 45 degrees slope angle is that we can blindly the open pits were running in olden days with the 45 degrees slope angle, overall pit slope angle 45 degrees, then it is okay. That is a thumb rule. There are no scientific studies and no monitoring at all. At that time, the depth is also low at around 50 to 100 meters. Now that we are going deeper and deeper, there is a need for the scientific study and monitoring of the slope, and no field validation. Even so many disasters happened, we couldn't learn anything from the past incidents, past accidents. What is the cause? How to avoid? We couldn't do that analysis. And if suppose there is a failure at one area, at least we need to analyze and what are the root causes for that failure. We should avoid that causes to repeat the same type of actions. Most of the cases, the same conditions are allowed to the accidents. So lack of risk evaluation approach. This is a new approach that there are so many contributing factors that I will discuss in the later stage, and experience and thumb rules. Only because based on the experience, like I told, that thumb rule 45 degrees in topsoil, the bench height should be 5 meters, and in hard strata the bench height is 10 meters. But 5 in weak strata and 10 in hard strata. This is the normal things we do based on the experience and thumb rules. So 4 guidelines for safe design and monitoring. There are no guidelines at all. Even if you see, if you Google the guidelines, are if you very in Australia they are following.
The sliding's not moving, sir. Sliding's not moving. Sliding. Sliding.
Telling about this need for the present study only.
Okay. Please carry.
Okay, 4 guidelines, and there are no statistical analysis. What are the major reasons and what are the root causes that are contributing to the slope failures? Parametric analysis are not there. Just even if you see the old studies, they just give the what is the factor of safety, what is the final overall pit slope angle. That is the major thing that we find in the slope failure study. But the study should cover all those things. What are the major contributor factors that is causing the slope failure? So many factors are there. What are the different factors? Out of these factors, what is the most sensitive parameter that we need to evaluate using this parametric and statistical analysis? And now ready-made formula. Suppose as we go deeper by deeper, so there may be suddenly a clay band, other thing. So in that situation, how to calculate the factor safety? Again, we need not go for the scientific study because it is a very costly affair, and for the time being, we need to evaluate what the factor of safety of that one. Because we didn't have to wait, we have to go deeper and deeper. We do not stop our production, all those things. So that formula we need, and lack of accountability. There are some indications because if you, all of us are money people are there, already learned people are there. So we indicate because of the production pressure from the top management, we ignore some of the indications of flow failure. Our food drainage system. During rainy season, we need to provide the garland tanks and seepage holes so that we can divert the rainy water to from away from the slope. So, as I said, no lessons learned from the past actions. So, all these are the contributory production pressure, organization culture, ignorance of the indications for fixing of the trigger levels at what level we should withdraw the persons, and deployment unqualified supervisors like outsourcing, and careless attitude of the officials because of the production pressure. What they do, they do, even they know because this is the major cause for this accident. So they don't go for that one because of the this pressure on them, and dependency on contractor. These are the root cause analysis of actions due to slow failure. What should be the objectives? The scientific study, how it should be. So scientific study should investigate the factors, and it gives the what are the factors that are contributing to the slow failure, and it should evaluate the stability analysis using the different methods. So validation is very important. Suppose if you use one method to validate that method, whether that program, that method, is it correct or not, it is giving the correct result or not, that we need to evaluate with the another different type of this. Like if you are doing LEM method, the limb equivalent method, then verify with the FEM method or other methods. That need to be done. And develop a statistical model. For every mine, you need to develop a statistical model so that the mine management using that chart or that model, they can calculate the factor of safety. And like that slope stability chart, you provide the management chart so that at this depth and at this angle, what is the factor of safety? So that type of slope stability chart need to be developed, and risk rating matrix that should be developed for each mine, that I will cover in the and finally that study should cover the guidelines. What are the guidelines that the mine management should follow? So that guidelines should be given by the scientific study. So as you know, even with the advanced technologies and no new softwares, again the accidents are occurring due to slope failure. So what we control, what we need to control, these are the three parameters behind our control. Because geometry we can control, but geology and groundwater we cannot control because it is already the strata. By manipulating the geometry, you can make the slope safer. So this is 3G geometry. The major factors that are contributing are the geometry. That means height of the bench, angle of the bench, slope of the bench, and width of the bench. Geology. If you do geology, what is the cohesion? What is the compressive strength? What is the internal friction angle? And what are the material properties, densities, like that? And the major parameter that is contributing the groundwater. That is, as I already told, that rainwater and groundwater is the major contributor in slope failure. So types of slope failures, even every slope failure, it will give sufficient indications, warning indications. Any failure doesn't occur all of a sudden. It takes some time. And it will slowly, that I will show with the figures also, it will slowly aggravate, and then it will result into the catastrophic failure. So that is a very, very important, that in the initial stage only we need to counter it and we need to stabilize it. Then we can avoid the major failures. So this is the slope stability analysis, because our aim of the slope stability analysis is not finding out the factor of safety. Our aim should be what are the reasons, what are the factors that are
కరుణకుమార్ గారు,
ఆయన వాయిస్ వస్తుందని స్లో వస్తున్నట్టు ఏదో బీబీ అందుగా.
Sir, it is not audible.
కరుణకుమార్ గారు,
Sir, ఇది okay.
it is not
సత్యనారాయణ గారి దగ్గర ప్రాబ్లం.
ప్రాబ్లం స్పీకర్.
సత్యనారాయణ గారు, it is not audible. Please
ఫోన్ చేయండి.
I think network problem.
అదే ఫోన్ చేస్తూ
సత్యనారాయణ గారు,
మీరు డైల్ చేసిన నెంబరు
there is some technical problem. Hello. కరుణకుమార్ గారు,
సార్ చెప్పండి సార్.
మరి ప్రాబ్లం ఉన్నట్టుంది కదా.
కాల్ చేస్తున్నాను ఒకసారి.
Hello. There is a network problem. Just I connected now.
Sir.
Okay. Hello.
Sir, it is audible, sir.
Now I am audible. Okay.
Sir, now it is okay, sir.
జాయిన్ అవ్వండి.
Okay.
రాజు గారు జాయిన్ అవుతారు. జాయిన్ అవ్వండి.
అది
బాగానే ఉంది స్ట్రెంగ్త్.
My screen is displayed or not?
ఆన్ చేసేది
ఏడా
సెమీఫైనల్ ఫ్రెంచ్ ఓపెన్.
Hello.
Sir, it is okay, sir.
It is okay. Then.
Yeah, Sachin garu, please continue, sir.
Okay.
Please
Thank you, sir. Okay, sorry for the inconvenience. Okay. Next, coming to the analysis, as I told that, so we need to develop a model and we give to failure mechanism
Sir,
I think it is
Sachin,
covered
Sachin.
or not?
Sachin గారు స్మాల్ ఇంటరప్షన్.
Is covered or not? No, sir.
మీరు ఇప్పుడు అంటే మాకు ఇట్ ఈస్ 11th స్లైడ్ ఈజ్ విజిబుల్ టు అస్, బట్ సెకండ్ స్లైడ్ నుంచి మనము అంటే కనెక్షన్ ప్రాబ్లం అయితే ఉన్నట్టుంది.
Okay, this I think again I will share it.
ఇప్పుడు
ఫస్ట్ స్లైడ్ చూసాము.
సార్ ఫస్ట్ స్లైడ్ ఓకే సార్, సెకండ్ దగ్గర నుంచి
No, I went to I'm actually I went to 10th slide. 10th slide. I
10th.
think
సార్
Yeah,
సెకండ్ స్లైడ్ నుంచి జస్ట్ చెప్పండి సార్, ఎందుకంటే మీకు సెకండ్ స్లైడ్ దగ్గర నుంచి మాకు కనెక్షన్ ప్రాబ్లం వచ్చింది.
oh, okay.
స్క్రోల్ అప్ టు ఫస్ట్ సెకండ్ స్లైడ్ సార్.
This one.
సెకండ్ వన్.
This is the first one.
దట్ ఇస్ స్లోప్ స్టెబిలిటీ అనాలిసిస్.
This one, okay.
మాకు స్లోప్ స్టెబిలిటీ అనాలిసిస్ అనేది విజిబుల్ గా ఉంది సార్ స్క్రీన్ మీద. ఐ థింక్ ఇట్ ఈస్ 10th స్లైడ్.
That is the 10th slide.
యా, ప్లీజ్ స్క్రోల్ అప్ టు సెకండ్ స్లైడ్ సార్. Yes sir, second slide. Now third slide is visible sir in the screen. Please scroll up to second slide sir. Yes. Now it is okay sir.
కంటిన్యూ.
Please continue sir.
Now okay sir.
Now it is okay?
Yes sir, now it is okay. Please continue sir.
Okay.
కంటిన్యూ.
So again I have to repeat all those things. Okay. As I said, the open cast mining, most of the production in India, even in other countries also, in India mostly 95%, other countries 85%, 75 to 80% from the open cast mining only, because the major it is a cost effective method, and underground mines are loss making, and the advanced technologies like from the exploration to transportation of the ore, you can atomize it because of the IoT technologies. Without manless drilling, manless shovels, manless dumpers, and manless trains also, that are operating in. If you go to Australia, that is a one mine. They are operating. Everything is with digitization only. By sitting in the room, you can operate shovels, you can operate drills, you can operate the dumpers. So that much technology, because of that much technology, and the mining is open cast mining is going deeper and deeper. We can see in future up to 1,000-meter depth also, because of the new technologies that we are inventing and discovering. So with that technology, we can increase. So lot of, if you see BCCL, if you go for ECL, and even in Singareni also, lots of blast making underground mines we are. If you see the pipeline, GDP pipeline and 5A, we converted into open cast mine. So like that, in BCCL, most of the mines they are converted into the open cast mines.
యువర్
So there is an increasing number of mines because of the outsourcing and because of this action. There are number of open cast mines are coming and private players are coming. So there is a risk because the private players they are not very much do not have experience in this method, and most of the even in Singareni in organized sector like government like Coal India also, most of the main the frontline operations are being done by the outsourcing people, contractors only. So these are all contributing to the high risk of slope failures and stability of the slopes. So if you go for if you see last 20 years, the major contributor factor in open pit mining industry is the slope failure. Even every year there are more than 30% of the fatalities are due to slope failure only. And if you see the disasters, disaster means one disaster means the definition is involving 10 or more fatalities, we call it a disaster. So if you see in open pit in India, there are 4 disasters. All are due to slope failure only. Amsa granite mine and Kulda OCP, Rajmali incident and Kavadi open cast mine. all these 4 open cast mills, the disasters are happened due to slow failure. This is the only single and major cause. So there is very much concern to do the to give importance to the slope stability. So the worst disaster in open pit mining is the Rajmahal, which involved 23 fatalities. If you see all the 4 disasters, there are 60 fatalities in the disaster. So these are the some cases. Even some cases like Juna Kunida, Dorli OCP, they are because of the indications, warning indications, they are already the withdrawn the persons. So it avoided the major disasters. So what are the rules? I have analyzed the around 100 slow failure cases. If you see the 100 slow failure cases, the major root causes are the unscientific design and poor monitoring. In the olden days, there are thumb rules like experience. If in topsoil, the bench height should be 3 to 5 meters, and in hard strata, the bench height is the 10 meters, and overall pit slope angle is 45 degrees. These are the thumb rules that we are that mines were operated based on these thumb rules. There is no even there are failures. We haven't taken the what are the root causes, and we have not implemented in the future mines like now we are operating the mines. So there are no guidelines, no risk evaluation, no parametric statistical analysis, no formula. If suppose we are going deeper and deeper, there is suddenly we encounter some clay band or some other strata, some big zones. How to we avoid this? How do we approach the benches at that location? We need to develop a ready-made formula so that we can apply the formula. Because again, going for the scientific study and analyzing all those things, it will take time, another 3 to 4 months. But for a running mine, it is not so easy. So we need to develop a ready-made formula for a mine so that they can calculate on the field and at the site itself what is the factor of safety in case there are the changes in the geomining conditions. So lack of accountability. Most of the cases because of pressure from the top management, and we ignore the slow failure indications also. So even some people supervisors, they don't have the adequate knowledge and are training on the slope stability analysis. What are the warning indications? What we need to observe daily in our routine, and what are the actions that are offered? We haven't learned anything. So same cause the slope failure is causing the accidents. So these are some of the root causes for the slope failures, and what should be the objectives? What to avoid these root causes? What should be the objective of the scientific study? So after the analyzing all these things in 2017, while amending the coal mines regulations, we made it a part of legislation. Now the scientific study and monitoring is the mandatory. Every coal mine, they should submit their scientific study report along with its monitoring methodologies, all those things. Now it made a mandatory. Previously it was not mandatory before 2017. Now the DGMS made it mandatory. So even if you see the scientific study, they should investigate the factors. What are the factors that are contributing the slope failure? What parameter is more sensitive to the slope failure? What parameter is the less sensitive? So there are different parameters like slope angle, depth, cohesion, internal friction angle, descent intensity. What is the most contributing factor to the slope failure? And analysis should be based on two different technologies, because we can validate one technology with another technology so that the analysis should be accurate. So for every mine, we should develop a statistical model and give it to the mine so that they can use that chart. That chart they can predict the what is the factor of safety in case of there is a change in the geomining conditions. So that chart, what at this depth, at this height of the bench, what is the at this pit slope angle, at this bench height, at this depth, what is the factor of safety? That type of chart, ready-made chart should be given. And for every study, what are the risk factors? What are the risk classification they should give? Based on the risk classification, they should analyze the conditions and give the risk rating matrix to the mine management. And at the last, they should, after this analysis, they should give the guidelines for operation and monitoring of the pit slopes. This should be all the 6 conditions should be covered in a scientific study. So as you know, even
Sir, please move the slides, sir.
yeah.
Sachin garu, please move the slides. Slides are not moving. Please move the.
So I moved it because of
It is still okay. Okay.
Shall I share it again?
With your audience, please move the slides. Sir. Okay. Okay. Now okay.
Now it is 8th slide. Okay.
Now it is 8, right? Okay. So these are the 3G: geometry, geology, and groundwater. These are the major factors that are contributing to the slope failure. We cannot change the geology and groundwater. Groundwater we can change it, but geology we cannot change it, and geometry we can play with our hands. So these are the factors that are contributing. So we need to concentrate on these factors and how to even in the geology also, how to stabilize that geology and how to drain up the groundwater, how to optimum design of the bench height and slope. These we need to do with the slope fluidity analysis. So as I told you, that slope failure doesn't occur at a time. All of a sudden it cannot occur. So it gives sufficient warnings. If you follow the warnings, if you withdraw the persons, we can avoid the catastrophic failures. So sufficient warnings I can show in the later slides how the slope failure will happen. So these are the different types of plane failure. This is already you can get from the literature also. So every analysis, first we need to develop the geotechnical model. From the mining plan, we take what are our different options for a particular depth. We model them and we give the input parameters like the material properties and bench height, bench width, overall slope design, overall pit depth. So we give it and we select the failure model. There are famous failure model. There are two more Coulomb failure model and Oken-Brown failure model. These are the famous failure criteria we use in the modeling. So these we can use any method. All are almost equal: LEM method, FEM method, and FDM method like flat slope, slide, Galena, and RS2. You can know ANSYS. These are the different softwares that are available using this based on the Oken-Brown failure model criteria. So by operating all the parameters, we will get the one final design with the acceptable factor of safety. So we implement that one. Suppose if there are slight indications, first we monitor and stabilize it. If it is a warning indications are there, so like slight crack or slight displacement is there, we can stabilize it. We can find out what is the reason for that one, and we can try to stabilize it, and we make it stable. Otherwise, if sudden changes, there are major changes in the, suppose there is sudden fault or clay band, other unstable conditions we notice, then again we need to do this analysis. Again, the processes we need to do. These are the different methods for slope fluidity analysis. What are the advantages? This we can get from the books also. What are the outcome? Factor of safety. We should aim at not only the factor of safety. What are the unstable zones? Where the
sir, slide move అవ్వట్లేదు సార్, కొద్దిగా slide move చేయండి.
Okay.
How it is in 8th.
9th చూపించండి.
అయిపోయింది 13th slide సార్.
Now it is okay?
Yeah, 13th slide is now.
మీరు
slide, yeah.
చేస్తారా?
Okay.
కృష్ణ గారు?
The 13th slide, sir. Now it is 13th slide is showing on the screen.
Yeah, I will show. Okay. Just otherwise, you can listen to ask them to listen to me because there is some gap between.
Yes.
Okay. The major outcome of the numerical analysis should be not only the factor of safety. What are the factors that are leading to slope failure? Where the unstable or failure zones that are happening within the this section of the strata that we need to observe. So most of the studies, if you see, they give the factors. That is not what are the major area that we need to concern. What is the strata where the failure is happening. That strata we need to consider. We need to stabilize it, like using the shaft plating, using the rope side bolting, using the cable bolting, like that we can stabilize it. So now I am going to the 14th slide. It is visible.
No, sir,
Is it
13 is visible on the screen.
Otherwise, I will do like this only.
Yeah, now it is 14 slide visible, sir. Yes, sir.
Okay, I do not go to the slideshow. Slideshow, it is not showing it. Otherwise,
okay.
I make it bigger. I will full screen and make it full screen.
సత్యనారాయణ గారు ప్రెజెంటేషన్ షేర్ చేయగలరా? అంటే అసలు చూడడానికి కామెంట్స్ చెప్పాలి కదా.
Sir, this is actually I need to publish some papers also, sir.
ఓకే, మరి మీరు చూపించండి. మీ కామెంట్స్ చెప్పాలంటే ఒక 9th స్లైడ్ నుంచి ఒకసారి చూపిస్తారా?
9th slide. Okay.
9th స్లైడ్ నుంచి ఒకసారి చూపిస్తే మేము కామెంట్స్ లాస్ట్ లో చెప్పాలి కదా. అది ఓకే, అక్కడి నుంచి ఏంటిది తగ్గించండి కొంచెం సైజు. ఒక స్లైడ్ ఒక హాఫ్, ఒక 10 seconds చూపించినా చాలు.
Okay, that's why, sir, I am not going for a slideshow.
చాలు. ఓకే, మీరు అట్లా టైప్స్ ఆఫ్ బిట్స్ ఫెయిల్యూర్ మేము రాసుకుంటాం అంతే. ఓకే. స్లో ఫెయిల్యూర్ అనాలిసిస్. ఓకే, టైప్స్.
These are methods for slope failure analysis, sir.
తర్వాత మెథడ్స్. Okay, next.
Advantage. This I am not explaining because this can be available in the literature because there is shortage of time. I will directly go to the case studies.
Advantages.
There are 4 case studies we took from the Singarini only, Godavari Valley coalfield, because this total analysis is in Godavari Valley coalfield from Kottagudem to Adilabad district, only OCP Karagura OCP1. So we covered unstable, the slope failure cases and the stable cases also. So there are 6 case studies. I will explain one case study because it is the time will not permit. So this is the location of the different mines that we took for the analysis. This is the around 254 kilometer stretch we have analyzed in this one. I am explaining the Dorli OCP1 case study. This is I went to that field. I collected the data, borehole data and samples. I analyzed it in the laboratory. I then estimated the properties by using the triaxial test like that, internal angle, friction angle, cohesion, density. Those properties are being used in the analysis. This is the satellite view of the mine and the maximum depth of the mine. Whenever when there is 120 meters, that is the maximum depth of that mine. So this is the different strata: soil, sand, clay, coal seam, sandstone. They are operating at the time 120 meters. 3 seam was being worked at that time. So 120 meters depth at that time. So this is the section of the working section of that mine. Overall principal angle is 45 degrees, and height of the depth of the mine is 120 meters. So these are the parameters that we got from the laboratory. Then using this Rackmoss property, it is converted into the Rackmoss properties. There are some softwares are there that will convert it into the Rackmoss properties. Using the more that is one equation is there. By that equation, we can convert it to the Rackmoss properties. In situ properties should be converted to Rackmoss properties before we are going for the model. Okay, Rackmoss properties means it will cover the this fractures, inherent fractures, inherent disturbances. It will cover. So always Rackmoss properties are lesser than the this in situ properties. So this is the 960 MRL, the surface RL of that mine, and 840 MRL is the bottom. And we need to, as it is, what are the strata, how it is exactly, we need to model into the modeling. Otherwise, we cannot get the even small clay panels should be taken, and inclination of the strata should be taken into the consideration. Then only we get the accurate results. So here most of the scientific studies, if you see, they do not consider the inclination of the strata. That is also one factor that is contributing to the failure of the slopes. So as I already told you, one method is not counter to revalidate, to validate or to counter. We need to take at least 2 methods so that whether our model is giving accurate results or not. So here I have taken 3 different methods for accuracy of the results or for validation. That is slide. First is the limit equilibrium method. Here we are getting the 1.38. Even in RS2, it is the most advanced technology, finite element method. Here we are also getting 1.38. And FDM, flat slope, where we are getting 1.39. Mostly the factor of safety is very close to each other. Because of their own unique process, their own limitations and advantages, disadvantages, they will, if there is any discrepancy in one method, it will be covered in another method. So because of they follow different processes, we need to validate with the other methods. That is very much needed. Okay, this is the an effect of the different factors. It will I will explain in detail what are the effects of this one in later slides. And this, if you see effect of water table, this is the water table at Dorley OCP1, this line. And if you added the water table, this 1.38 suddenly drop to the 0.93. Okay, this is the 40 meter. The failure is at from the crest. The failure developed at a distance of 40 meter from the crest, and the failure is occurred at a depth of up to 50 meter. Why 50 meter? If you see the data, the borehole data, see there is a 33 meter clay is there, and 8 meter sandstone, 7 meter soil. This is the very weak zone. The failure is happened in this weak zone. This is the weak zone. If you see, this is the failure. So this is the at a distance of 40 meter from the crest and at a depth of 50 meter, the failure was happened at Dorley OCP1. Now we go to the actual scenario. Actual what happened, that we with the photographs I will explain it. And this, if you see, this is the overall pitch slope length of 45 degrees. Okay, this is a 50 meters weak strata, and topsoil clay is there. This after 50 meters, if you see, if you observe this, the benches are intact. This 50 meter strata after failing, it is overflowed over the R strata beneath it. Okay, this is the crest, pit crest. From the pit crest, the crack was developed on 4th June 2014. One crack was developed. See, these are the different stages. First, crack was developed on 4th June 2014. It get widened and deepened in on 17th after almost 11 days. Because what I mean to say is, before the failure, it will give sufficient indications. There are sufficient warning indications. So we need to get that warning indications. We need to stabilize the strata. So like that, it gets widened. And if they are monitored with the total station also, there is a horizontal displacement of in stage 2, horizontal displacement of 0.225, vertical displacement 0.6. Finally, when it failed, the crack got widened to 2.765 meters and 5.24 meters.
టీ తాగుతానంటే వస్తా.
So this is the indication.
మళ్ళీ తాగుతారా?
Dear participants, please mute your mics, please. Dear participants.
So the crack got developed on 4th June 2014. Means it took almost 4 months. 13/10/2014, there is a catastrophic failure. Means it has given sufficient time. Over the time, it got displayed, it got widened, the crack got widened and deepened. Finally, the slope failure occurred on 30/10/2014. So, if you see this, the horizontal displacement, different displacement, stage 2, stage 3, stage 4, stage 6. Finally, the displacement, horizontal and vertical displacement, the cumulative displacement is raised up to the 5 meters. After 5 meter of vertical displacement, there is a catastrophic failure. And during that period, if you observe that 13th June to 4th June to 13th October, there are heavy rainfall is there. The why I am to means every factor we need to evaluate to actual what is the actual root cause of the failure. We need to analyze everything. See if you see there are the Garland, there is no Garland drains. The seepage of water rainy season, it will flow through the benches, and there are some gutters are formed with the benches. The water was accumulated at the bottom. So crack was developed like this only, and gullies are formed due to flow of rainwater. So finally, the water was accumulated at the bottom. So there are no proper drainage system. There are no garland drains. There are no seepage holes to drain the groundwater. So at that time, the rainfall was also, if you consider the rainfall, continuous rainfall for 11 days, and final up to around 1200 mm rainfall was occurred within those 4 months. So that is also one contributing factor to the slow failure. So after doing this one, okay, that was happened. Then what we need to do? So slow failure occurred again. We have to run the mine. So what should be the this bench slope angle? What should be the bench height? Like that overall slope angle. At what slope angle if you move, then we will be stable. So that analysis we did, and analysis after analyzing the factor of safety at 1.22, the slope overall pitch slope angle should be 32 meters. So 32 degrees slope angle is best for that mine. So by doing this parametric analysis, by changing the slope angle, we have got the one final optimum slope angle is the 32 degrees. With that, the mine was operated Dorli OCP1, and if you see, this is the failure and the benches that worked during the 2017 and 18. This is the slope benches. So with the overall pitch slope angle of 32 degrees, without any failure, the mine was operated. I think it is closed in 2019 or 20 due to lack of results. Okay, this is the ultimately with the analysis, with the slope stability analysis, we got the optimum pitch slope angle at what that mine should run. So these are the, so if you do the vertical displacement through stability analysis method, that FEM method, here vertical displacement of 5 meters is there, horizontal displacement is 3 meters. So these are matching with the actual situation. Actual, if you see here, I will go to that slide, this slide. So if the vertical displacement is around 5.25 and horizontal displacement is around 2.75. So almost the modeling results and the actual field results are matching with you. This is the vertical displacement. If you see this figure, you can get it. So almost that, what I mean to say is that always field validation is very, very important to get the accurate results. So this modeling results are matching with the field results. So our model is accurate. So finally, this is the conclusions of that mine. Now coming to the sensitive analysis using SPSS, that statistical analysis, the separate software is there, which there are 5 different major factors. One is, as I told you, what is the pitch slope angle. Another one is the density, cohesion, internal friction angle, and the groundwater. So out of these, the groundwater is the most influencing factor. So what is the this relationship? How it will influence? If you go to the overall pitch slope angle, it will influence like a exponential. The relationship is exponential between the factor of safety and the overall pitch slope angle. And the internal friction angle and factor of safety, it is also exponential. And density and this overall pitch depth, slope height, it is almost a power. The relationship is power function. And cohesion, it is a linear equation. For cohesion, it is a linear equation. So this type of equations we need to develop. And for this one, there is not much time. There are different methods. Whether this statistical analysis is correct or not, it is statistically significant or not. These we need to correlate with the R square function. If you see these are equations, there are different factor of safety versus density versus cost. There are different predictive model are developed with the single factor. If you change the, suppose if you change the theta, oral pitch slope angle, it will major impact on the slope stability. So like that, there are the these are the power function, linear function, exponential function, and power function. These are different relationships with the factor of safety. Why these are accurate? Because the R square value is more than 0.95. So these relationships are accurate. So these are the different. I need not to go in depth because it is a PhD level. This is row correlation coefficient, non-linear regulations. These are all our parameters to validate the statistical equations. We need these parameters. So finally, we develop a ANOVA analysis are there. So different because as I said already, there are different parameters are there to validate the one factor of safety. So if you use these, all these are, so most of the analysis they take only one parameter, they are like R square value. If it is more than 0.7, then our my formula is okay. That is not sufficient. We need to evaluate with the different. This is if you see the model evaluation. I have taken the coefficient R square value. I have taken the ANOVA. I have taken the student's t-test within the 95, whether it is coming or there is a root mean square value is there. And the predicted model means that statistical analysis and the numerical model. Both are matching, whether they are matching each other. If you see the black line is there, this is measured one. Measured means that is got from the numerical analysis. That is got from the FEM analysis. And this statistical analysis, we get the red one, predicted FOS. These are exactly matching with each other. So my formula, whatever the factor of safety I got, that we got for this particular mine, this formula is accurate. So with using this formula, if there are any changes in the cohesion, any changes in the density, or if you change the overall pitch slope angle, then you can get the direct factor of safety without going for the scientific analysis. Because it will take a lot of time, at least minimum 2 to 3 months. So by using this formula, you can get this is a ready-made formula. By using this formula, if you just substitute the parameters, you can get the factor of safety of that particular area. So even you need to, if there are any joints, what are the effect of the joints on the slope failure that need to be evaluated using the kinematic analysis. I don't want to go into depth because it will take another 30 to 40 minutes to explain these scatter plots. So first we need to do the kinematic analysis, whether the effect of the joints are there on the slope failure. If there are generally because of the effect of the joints, the toppling wedge or planar pillars will occur. So the joints first what is the process? First, we need to do the kinematic analysis. We need to rule out whether the effect of the joints on the slope is or not. Then we go for the numerical modeling. So these are the because this class will take 3 to 4 hours actually. So the unnecessary things I'm skipping all those things. Okay, this one. These are the different impact of different factors on these 6 mines. What are the 6 ones that are studied? If you see here, water table, addition of water table, the percentage of change in percentage decrease. This minus indicate the decrease and plus indicate the increase. So if you see almost 10 to 33%, the factor of safety will be decreased due to increase in the water table. If you increase 1 meter water table, that will affect the around 10 to 33%. So the most sensitive factor is the water table. Next comes to the internal friction angle. Next the unit weight. Next is the slope angle. So the sensitivity ratio is the most major factor is the water table, and least factor is the cohesion. Cohesion, if you take, there is a very least change, the 0.1 to 0.29. So if you see all these things, the major factor is the water table and least factor is the cohesion. different for all those mines, the optimum pit slope angle design mostly is even Ramagundam OCP. If you go and see, it is operating at 38 degrees only. If you calculate the overall pit slope angle, if you go and see, that mine is operating at 38 degrees only. So these are the different shape optimum pit design that we suggested, because as I went there, I took the sir very much know that Ramalingam sir no, because he has given permission when he was GM sir, he has given me the permission to take the samples from the mines and to do the analysis and to get the data from the mines. So it took almost 6 years to study. For individual mine, I have suggested a factor of safety for that particular mine. That one formula that can be used directly by substituting the parameter, they can get the factor of safety without going for the scientific study. So this is a chart that I want to all the scientific agencies to suggest for each mine. So by seeing this the chart, we can get the factor of safety. Suppose this is the slope height. Suppose I want to know what is the factor of safety at the 200 meter depth and 50 meter 50 degrees of pit slope angle. These are coming around 1.4. So by seeing this one, we can directly get the factor of safety. At a particular pit slope angle, at a particular slope height, what is the factor of safety? By seeing this chart, if you provide the mine management, they can get the, because as the mines go deeper and deeper, the factor of safety will vary depending on the slope, the depth of the mine and pit slope angle. So this type of chart should be suggested in the scientific study. This one is very important, because that is one part. The scientific analysis is the one part. Based on the scientific analysis, we cannot 100% avoid the slope failures, avoid the dangers due to slope failures. We need to do risk analysis. That what we implemented in as a DGMS, we suggested for the safety management plan. In safety management plan, there should be a separate chapter for this pit slope analysis. What are the factors that are contributing to the failure? What are the risks that are contributing to the this one? So this is the risk analysis should be complementary to the this slope failure analysis. Risk analysis combined with the slope failure analysis, that is the 100% we can avoid the this slope failures. So there are so many factors that are concerned risk rating criteria. For developing this also, I have published one paper on this also. I took around 100 slope failure cases. Based on the 100 slope failure cases, what are the principal factors and what are the operational factors, what are the historical factors. So there we broadly categorized into 3 different categories, and based on the 3 different categories, we give some rating on a scale of 1 to 10 and on a scale of 1 to 5. Because the major, what are the major contributing factors, major risk factors that we took, the scale is 1 to 10, and the operational factors and historical factors, the scale is 1 to 5. So based on that, if you see this overall pit slope angle is the major risk, bench angle, geological disturbances, depth of the mine, groundwater, and scientific study design. If you take, this is the scale is 1 to 10, and what is the number of slope failures that are occurred, because depending on the, suppose I will take the one parameter, that is the pit slope angle. If it is a less than 30 degrees, we take the risk rating is as a 1. If it is between 30 to 45 degrees, risk rating should be 5. Why I took the value, numerical value 5? Because in the history, there are 20 slope failures if the 32 degrees to 45 degrees. Bench angle, overall pit slope angle 30 degrees to between 45 degrees. There are 20 slope failure cases. Next, coming to the 10. If the overall pit slope angle is more than 45 degrees, 10 out of the 12 mines with more than 45 degrees, there are slope failures. So if the slope angle is more than 45 degrees, it is more out of 12, 90% of the cases there are slope failure was occurred. So the rating is given 10. Like that, for every parameter, depending on the history of the slope failures, analysis of the slope failures, the rating was given. So if you see the scientific analysis also, there are 16 slope failures. One is going, if there are, so even there is a scientific study in 16 mines slope failure occurred because they didn't do the risk rating analysis. They didn't analyze the risk rating parameter. So not only the scientific study, we need to do the risk rating and combining these two, then we can avoid the this failures. So even 16 mines, those are the scientific study reports. In those cases also there are slope failure, and 69 mines there are no scientific studies. In all the mines there are slope failure. Slope failure means not only overall big disaster. One, if you single bench fail, that is also considered into the slope failure. Even some of the pieces overhanging, if it shoots some chunks, it shoots some because of the pressure, that will also come under the this slope failure. So these are the different major factors. There are 6 major risk factors. And coming to the operational factors, if you are monitoring, then you are safe. If you are providing good drainage system, then it is safe. If you are following control blasting system, if there is no blasting, then it is safe. Even if you are going for the deep hole blasting, if you are doing control blasting, then it is a safe. Mechanization, if you highly mechanization, like if you use the IoT technologies, if you avoid the manual intervention, then it is all those things should be considered during the operation. Slope monitoring, drainage system, blasting practices, and mechanization. Coming to the history.
Sir, Sachin, sir.
Yeah.
Sir, second panelist is also waiting.
That's why I'm skipping.
I will
This is
start,
the
7:30.
okay.
Yeah.
Shall I close now?
Yeah, with your concluding remarks, you can close, sir.
Okay, I will conclude the concluding remarks. These are the risk rating matrix that every scientific study should propose this risk rating matrix for an individual mine. Coming to the correlation between the risk rating matrix and scientific study, that should be done. For that correlation, I have analyzed around 15 cases of numerical study of the 15 cases, and that we got the factor of safety through the numerical study, and we correlated with the risk. This is the different mines, around 13 mines we took for the correlation, because if you have a lot of data, then your results will be accurate. So 13 mines, what is the risk rating? What is the collective risk by combining these all those 15 parameters? If you, this is the rating by giving the rating for individual parameter of the for every parameter of 15 parameter, then we get the, if we combine the total risk, then we will get the this factor. So condition of the slope, where if you take the total risk 81 more than 70, in all the cases the factor of safety is less than 1. Up to 72, the factor of safety is less than 1. Means, what do you mean? If it is if the total risk is more than 70, it is high risk, because the factor of safety is coming less than 1. Means, if the total risk is more than 7, then there is definitely a slope failure. So like that, if the factor of safety is less than 40, then the if the total risk is less than 40 and the factor of safety is more than 1.2, so that is more safe, stable. So like that, there is a risk classification empirical guidelines. You can use this empirical guidelines. High risk more than or equal to 70, factor of safety is less than 1.2, then there is a high risk, and medium or acceptable risk is if the collective risk is 30 to 70, then that is acceptable risk with some, because we cannot avoid total risk. We with the some, by taking some risk we need to operate. Otherwise, we may enter into the losses, because even if a single degree of the single degree of the steepening of the slope, it will you need to remove the vast value of the this overburden. So the optimum is very much important. We need to take the calculated risk for operation of the mains safe and profitable operation of the mains. So this is the risk rating. This is the conclusions over the major poor design, poor slope monitoring, rich data, lack of knowledge, lack of guidelines, risk analysis, poor risk analysis. These are the major factors that are contributed to the slope failures. With the different factor of safety. So the optimum design, optimum pitch slope angle is the 31 degrees to 35 degrees if the height varying from the 120 meter to 200 meter. If the height increases to, this analysis I did for the RG42. If the height increases to 407, then the slope, overall pitch slope angle we have to decrease to 29 degrees. So the simulation results of the three different methods, they are coming within the 1%. The accuracy is, error is within 1%. So it means the models are very accurate, and models are more sensitive to some factors like groundwater, frictional angle, and less sensitive to some factors like I already told, position. So for the from the Kottagudem to Adilabad, there are different strata conditions. This formula can be used for the to ready to calculate at the so this is the because of the time constraint, I need to finish it. I couldn't explain in detail because it will take another 2 to 3 hours to explain everything in detail. So with this, I conclude this presentation. Thank you very much. Thank you very much for giving this opportunity. Thank you, Brenda.
Thank you, sir. Now I request
Thank you, sir. Thank you.
Ramalingeshwar Garu to moderator for this event to continue.
Thank you, Janakram Garu. So incidentally, I joined with him from his office. So for this webinar, it is a very initiative taken by the chairman of this Kottagudem chapter, Institute of Engineers, Janakram Garu, and Secretary Tarun Kumar Garu. So I was asked to join as moderator. Thanks for the opportunity given. And the speakers, present speaker is ISN Garu. He is our friend, our present DMS. So he worked with us in Singareni. I was agent and he was district manager. So he's done a lot of good work for his research. So it is evident from the presentation that 6 years study he has done in 6 mines of Singareni, open cast mines. And the design and stability analysis of open pit slopes in coal mines, a case study. So his introduction, very well presentation, consisting of 35 slides. He told that he is presenting the research paper. So presenting the research paper, and introduction is given that major production is coming from the open cast mines, more than 90% in India. And there are different disasters in recent coal mines, open cast mines. There are 4 disasters. Which was major is the Raj Mahal 2019, where 23 disaster fatalities have occurred. So, like that, various problems he narrated in open cast mines. The problems are due to slope failure and the daylighting and the high wall risks and more concentrated workings in OC mines. More accidents are occurring. More than 30% are due to slope failure. And the need for study of slope failure is reiterated by him to reduce the accident rate. And he observed that 45% slope angle generally, without study earlier, the mines are being run. So generally they are keeping 5 meters top soil bench height and 10 meters in hard soil, and 45 degrees is the angle. So as per depth also they were keeping. Now after the scientific study, proper bench height, width and angle of slope are being maintained. And the objectives in the so various topics he has covered in the presentation. So they have done modeling and modeling also. In 6 months they have conducted different studies. Various parameters were affecting such as geology, geometry, groundwater, etc. 3 parameters. So that is 3G approach what he told. So then various failures they have studied, and one mine they have taken Worli OC2 as one mine, and they have studied in detail, and different parameters of topsoil, clay, sandstone, coal, and different layers they have studied, and different parameters such as cohesion, friction angle, and unit weight, and other parameters also they have studied, and modeling, numerical analysis also done, and they have done what is the root cause analysis, root cause failure for Worli OCP. So they observed that okay. So modeling results also they have nicely presented, and for the 6 months also analysis, sensitive analysis has been done, SPSS software, and also NAVA analysis also has been done, and finally what they have concluded analysis is final pit slope angle, how much it should be done, and they have done the risk analysis also, risk rating matrix also they have made. And finally, what they have concluded is slope angle shall be, and for Worli OC2, they have measured and came to a conclusion safe angle is 32 degrees. So what they have told 45 degrees is not, it is very risky, and different ratings also they have told 1 to 6, 6 parameters they have shown, and different rate angles also done, and the simulation methods, LEA, FEA, and PDA methods also done. Finally, this paper is very good and very well dealt. Very good research work done for 6 years, more than 6 years in Singareni. He is a son of the soil in Ramagundam, based GDK 5. He worked with me. So very good presentation done, very nice job done, and Institute of Engineers, you have presented a very good paper. Very congratulations and all the best, Satyan Garu.
I request Karunakumar Garu to introduce the panelist 2, Vikram Garu.
Sir, okay.
The time is
So we are
running
moving.
short.
Yes, sir. Thank you,
Very great.
Satyan Garu. You get the great, you are privileged, great, excellent inputs are given for the audience. Now I am requesting the panelist 2, Sri Kinal Vikram, a senior research fellow in IIT ISM Dhanbad. He is presently pursuing PhD as a senior research fellow at Indian Institute of Technology, Indian School of Mines, Dhanbad. He is expertise in mine occupational safety, health and ergonomics, planning and mining methods. He graduated in mining engineering from the JNTH in Telangana state and acquired a master's degree in mining engineering from the IIT ISM Dhanbad. He was the gold medalist in master for the batch of the 2017 and 2019. He was also a topper of the bachelor degree in the mining engineering. And moreover, he obtained 93.33% of marks in SSC. He published 5 research papers in a peer-reviewed international journals and presented 3 papers in the international conferences and 1 in a national conference. He has delivered 5 expert lectures in India. He gave the expert lectures for the DGMS official recruited in the year 2022 at IIT ISM Dhanbad. He was offered for the prestigious sandwich program from the Curtin University, Australia. He was the DGGC member at IIT ISM Dhanbad, and he also an associate member of the Institute of Engineers of India. Thank you, Mr. Sarikanal Vikram. Please, I'm handovering this session to you. Please carry on, sir.
Thank you, sir. Thank you. Firstly, congratulations to all you, sir, for establishing this local chapter, Institute of Engineers at Kothagudem. I welcome you all for the presentation. Sir, is my screen sharing is on, sir?
No.
Am I audible, sir?
Hey, you are audible, sir.
Okay, sir. So, is my
Yeah,
screen
now
is
it is, yeah, visible, sir.
Thank you, sir. So, a warm welcome to you all. And today's I'm going to cover a basics, an overview of open-based slopes and modern technologies for analyzing stability. So let me show what the content I'm going to cover in this. So firstly, I'm going to do one motto on this presentation. So there are a lot of value method and value technologies. The traditional methods were there, mechanical methods were there, numerical methods was there. So a lot of the methods were there for stability analysis. So here the question rises. So what are which method to adapt for which type of geology? Because the slope always, because slope stability always depends on not on a single factor, it's a multiple factor. So as it was a multiple dependent factor, it's not, we can say that this method is suitable for this and this method is suitable for this. So what I try to do in this presentation is, let you go through the basics of the slope stability and what are the failure, how the failure mechanism will takes place. And then after come to the traditional methods available for slope stability analysis, then I go with the advanced methods like numerical modeling, like a finite element method, finite difference method, differentiate element method. So then I come to the more technology like hybrid methods, with a combination of both traditional methods and numerical methods. Then I take a case study of small one case study. So this is a very small case study, and I don't take much time on this case study because of the analysis part I have already covered by the panelist one, which Dr. Satyanarayana sir. So I will give an overview of this case study and what are the slope monitoring systems, what are the monitoring systems available for the case study, and what are the lacking in that case study, and what to be done for overcoming the case study, right? And then after I go with some mitigation measures, so and a risk management system, what to be implemented, and what are the monitor systems to be developed, and all this. Then I go with the conclusion remarks. So let me go with an introduction. So also we know everyone, today's 97, approximately 97 production is coming from the open cast mines. So as this production was increasing, and as previous panels have told that we are going to the deeper and deeper and deeper. So if we now approximately it is around 250 to 300 meters. So if you go around 600 centimeters, then there comes the matter of removal of OB. So lot of amount of OB has to be removed, and this OB has to be dumped at some other place, and it becomes such a huge volume of OB. So stabilizing these OB will play a vital role in not only in terms of running the mine, but not only in terms of mine, it also creates a problem of social issues when it comes to the operators or environmental systems problems. A lot of issues was there. So I'm not going to in the details. So generally, while we develop a slopes or bench, whatever it might be, there are few parameters should be, we have an overall or as a brief idea about that one. That is one, geology, what the type of nature of rock it was, and what are the parameters, whether discontinuous there or not, or fault was there, what are the strength it was, and what the density, porosity, moisture content, all these parameters plays a vital role in stabilizing the slope. Then comes to the hydrology. See, in the previous panelist told that water is a very sensitive, water column is very sensitive to the factor of safety. So this is another important factor to be taken care of. Then comes the soil property. So what are the soil properties? This plays an because a lot of what are the modern techniques out there, all what depends on the soil properties. So this comes the cohesion. If the two particles are there, there's an attractive force between them, how attractive they are. And then comes to the internal angular friction. These are very two important parameters that by which the most column is developed on this basically two parameters. So these all the few important parameters to be taken care of. And later on, this one general topic. So 1901 to 2016, there are taken 23 accidents only on the Bruza slope failure. In that 143 fatality was taken place from these 23 accidents. And these are the few accidents which has taken place. I'm going to show you the slides. And willingly, mindfully, I have neglected the open cast of this Raj Mahal open cast fatality, because everyone knows what happened over there, because that one happened mainly to the lack of human error, and there's no proper inspection of this OB, no scientific studies were taken place, and there's no one is taking care of this. So that's a different case, so I'm not going in that. But what are the actions taken in the rest of the mines are shown here. These all the mines action taken place have their scientific study. They're noting that there is no scientific study conducted on the dams or not on the bench height stability, nothing there. They have done the analysis, and they have got approved from the DGMS. Then only they were maintain this mine. But though the actions are taking place, even the previous panelists, they had told that though the scientific studies has taken, 16 accidents has taken place. So this raises a question: why has accident taken place? So this is a very important question. So this my presentation entirely revolves on this, because as per my knowledge, subject to a correction, what I want to mean to say is, what are the type of analysis to be adopted for certain type of cycle, because this all the OB is very complicated structures, a lot of influence factors was there. So for each and every, we cannot implement all the we cannot use all the parameters in one analysis. So different methods we will discuss later on. What are the different methods was there? Each and every method has its own advantages and limitations. But the problem, as I told you, the problem is what type of analysis method to be implemented for particular type of geology. So that's what I'm going to discuss in the later slides. So here comes the parameters affecting the slope. So first one is slope dump geometry. So here comes the factors like height of the pinch or the dump and slope, zonation, what are the potential failure surface, what type of geometry was there. And next here is a second very important topic is foundation strength. See, as per of my knowledge, there are very few mines have done scientific study on this foundation strength, and there are very few, a lot of cases the dump failure had taken place due to the construction long place. There's a very less foundation strength. They conducted the dumps on that, so that causes the failure of the dumps. So less like in the foundation soil was depth, and it concerns the moisture, what are the grain size or density, all these parameters also and takes place. Thereafter, groundwater conditions. So what are the level of groundwater, and what are the rainfall, what are the vegetation, topography, what are moisture content in that dump or slope. So these also plays a vital role. Next comes the soil strength. So this one is soil percentage. What is the soil percentage? In the soil which was developed, the amount of soil, because soil is very soft nature and usually tends to slide. So this causes the instability in the dumps. So these are very important parameter. And the second one is slakeable rock. What is the slakeable rock? Generally, what is there when the extraction is or blasting some other taking place, it will the hard rock which was there is broken into very fine particles. That is called slakeable rock. So next one is minerals. So what are the OB was there? What type of composition it was, and what is the composition taking place, and what if we consider more of a shale, it easily the slope will fail. And that's not the grain size, and this is another important factor. As the grain size increases, what happens is generally it tends to slide, because reason this as the exposure of area of each the particles which was there, the cohesion will decrease. So next comes is moisture. This is a known factor. As the moisture increases, definitely the strength will be reduced. And weathering conditions, segregation of the rock, all this will causes the reduce in the shear strength. And next comes the very important mining methods. So there are three types of, not I'm talking about this open cast or the type of mechanization you've taken. These are extraction of the coal. So this comes to 3 million, then a strike cut extraction of the coal advancing down the dip. And second one is strike cut, the advancing up the dip. So third one is dip cut along the strike. So all these three methods, the best one is dip cut along the strike, because due to the reason that the extraction will takes place along the dip and the mine advances to the strike direction. But the problem here it is, as we go in this direction, the problem rises in the production. So when compared to other two methods, this has very less capable of production the huge volumes. So due to this advantage, most of the mines now are adopting only about two, whatever suitable conditions, the about two methods were adopted. Then comes the dynamic force. And all we know that due to the large blasting, open cast express a huge blastings. So due to this huge blasting, the seismic energy was developed. That's what I call as vibration, right? The vibration, as the vibration passes to the underground, what has happened? It will dilute the strength of the spoil. And next one is seismic. This is an earthquake. In India, very few cases. There is no, I think, no case was there on this. But still, when it comes to the abroad countries like very earthquake, like Indonesia, right? So in those places, this seismic activity plays a vital role because generally earthquakes takes place and rock distributions will takes place, and a lot of faults was generated, discontinuous generating, and that's causing the dump failure. So here comes the mechanism of failure. So how generally the dump field fails actually. So we all know that a basic of this failure. So when the increase in the shear stress and reduction in the shear strength along the failure plane. So that's causes the failure in the slope. But here comes the two types of failure was there. There's whatever the mechanism I will explain you later on. But remember there are two types of basics on this. So one is along the what are the forces acting on horizontal and vertical of the plane, and second one is around the we call it the along the linear not linear force causing the angular change in the soil. Because when it comes to the circular failure, this becomes a very important because moment of inertia is plays a vital role in the circular failures. And when it comes to plane failure, wedge failure, these places will take the failure takes place on the causes of the horizontal and vertical forces. Right. This will be discussed in the later on slides. So this is a very general phenomena of how this factor safety will be evaluated. So factor safety will be evaluated based on this Morse Coulomb criteria, and we as we know that shear strength by the shear stress. So shear strength is evaluated by using the Morse Coulomb criteria. This formula is shown here. The shear strength is cohesion plus a normal stress plus tan pi. The pi is an interangular friction, and C is the cohesion, and sigma is the normal stress. And this second equation which is shown here, that's when there is an water pressure. So when there's the water column was there, so it will obviously it will reduce the shear strength. So this was a formula for this. S is S plus sigma and minus U at tan pi. Here U known for the pore water pressure. So whatever the dump slope stability analysis was taken, all were the stability based on the concept of limit equilibrium method. So what is this concept of limit equilibrium method? So generally, limit equilibrium assume that when the shear resting along the and assumed failure equals the shear strength of the dump, which means generally in a normal simple terms, which means factor safety is equal to 1. Right. So what actions is whatever the driving force or what causing the failure of the force was there, that is equal to the shear strength. Right. This was the meaning of this concept of equilibrium. And here are the few formulas for this. This one already I explained you. The factor of safety is equal to 1, and shear strength by shear stress, that is equal to 1. So generally in the mines, we all know that if you want an approval from the DGMS or whatever it might be, so the factor safety should be between 1/2, 1/4 in the open cast mines. This is as per the William mine in 2004. And these are the very basic failure. For the first one, the basic failure is plane failure. Here you can see the video how the plane failure takes place. Right, the sliding block rests on the discontinuous and it slides once the shear stress that acts on the discontinuous plane becomes greater than the shear stress. So what I mean to say is, when there is the horizontal stress or vertical stress was greater than the strength which is had, the failure will take place. This failure will take along the plane. And second one failure is wedge failure. And this is another classical example where the wedge failure occurs in the rock mass with 2 or more sets of discontinuous. Right. So when the plane failure we talk about it is just it consists of only single failure. When single discontinuous there, it becomes a failure around that single failure. But when it comes to the wedge failure, this consists of 2 or more sets of discontinuities. So along those 2 sets of discontinuities, the failure takes place. So here is an image of this here. It shows there's a wedge failure of a rock. So here clearly you can see there is a horizontal wedge failure, sorry, horizontal discontinuous and the vertical discontinuous. So the causing the two discontinuous there. So this causing the failure of the surface. And next comes this is circular failure. This is a common failure where the OBUs were there of made of soil. And if you clearly see this, the sliding from the slope causes the hits the movement to the dumper, and this causing the what will I say the all rest of the whatever the wedge failure or planar failure. This causes more damage to the other people or machinery in the mines. So this should be taken care of. And next one is toppling failure. This is a failure when the lot discontinuous there along the steeply discontinuous structures and causing the toppling from the surface of the place. So this will takes place in the not continuous at one by one, it will takes failure. So what are conditions to be actually causing the toppling failure? So the condition here it is shown is there's a width and the height which is shown here is less than the tan theta. The theta is the dip of the slope. So if the width by height of the ratio is less than 10, then only toppling will take place. Means that failure takes place on the toppling side, top side. And when the width to the height of this less than the tan theta and the angle of dip is greater than angle of internal friction, then toppling with sliding, right? So toppling takes place along with the sliding. This is the combination of toppling failure along with the circular failure. And next comes the another criteria that the width to the height ratio is greater than obviously tan theta, and this angle of dip of slope is should be greater than the angle of height, right? And when it comes to this width to the height of ratio greater than and the angular dip is less than the angle of internal friction, no toppling and no sliding will take place. These are the few criteria how this causing only toppling failure or toppling failure with the circular failure or only sliding so it takes place. The sliding is just what is a planar failure. Right. And this is another composite failure, which is a combination of all the failures like plane failure, wedge failure, and the toppling failure. See, this is the most common phenomena in the coal mines. When it comes to the coal mine, this is the most common phenomena. So the combination of all these failures. And another important failure was there. This is a combination of active and passive failure. So this is the what I will tell you is when dump slope, particularly when dump is of weak rock and slope is steeply digging, acting wedge failure takes place. So these involves of the two wedge failures, right? So if you see this, the active plane which was there, it was causing actually this failure, and this causing the to outward direction of this. What are the remaining wedge was there? This was going to the outward direction, moving in the outward. This was in inward direction. Just moving to the outward direction. This inward movement causing the other wedge which was there, causing the failure of this outward to the outside direction and causing the accidents. And here comes this overall limit of equilibrium methods, right? So there are various methods was available. So how actually, and one more thing I need to say, how to decide whether the slope will take a failure in the planar failure or else in the circular failure or else in the wedge failure or else the toppling failure. How we come to know actually? So for this, we have to do an analysis called the kinematic analysis, right? So kinematic analysis in that there's a the graph called stenograph. So here I'm not showing you because it's a huge topic to cover, but I give the basic idea what how to know whether it's type of failure. So using the stenograph, there are various, just I explained to the width to the height ratio, the conditions are there. So if the certain condition was there, then it causes the toppling failure. So for example, if the principal plane stress was within the plus or minus 20 degrees relation. So if this is within the range, then planar failure will take place. So similarly for a circular failure, there's another criteria and all this criteria. But how this criteria developed? This criteria was developed using the stereographs. So stereographs, for developing a stereograph, mainly two things should be there. One is the direction of this discontinuous, another one is internal angle of friction. So these two parameters are required, and what is the direction it was there. So if you draw on the stereograph planes, then you come to know what type of failure will take place. So okay, fine, if you doesn't know the kinematic analysis, because everyone is not capable of doing those. So what other technology were? So there comes all these methods. What are the limit equilibrium methods? So as I previously explained, limit equilibrium methods were evaluated based on two types. One is moment of inertia, that means where on the inertial circular, and second is horizontal and vertical forces. So here comes the ordinary method of slices. So what this is, suppose if a slope was there, the slope was divided into various vertical blocks, right? So with these vertical blocks were divided, and these vertical blocks was we are known to the what are the vertical forces and what are the horizontal forces. So knowing these two, we will develop these balance the equation with the summation of horizontal forces equal to summation of vertical forces. So from this we will get the factor of safety. But what the problem with this ordinary method of slicing is, here ordinary method of slicing there is no inter-slice forces. What means, well, we already told you they were divided into various vertical blocks. So if they're divided into various vertical blocks, obviously it should be there the horizontal force as well as the vertical forces in the internal blocks. But this method won't consider those internal blocks horizontal vertical forces. So this is the limitation of this one. And next comes the Bishop modified method. So what is Bishop modified? This is similar to the ordinary method itself, but this Bishop order includes this ordinal methods forces. But here also another lacking with this method is it won't consider the inter-slide shear forces. So because we know the failure because takes place most of the shearing causes. So this is neglecting the shear forces. But generally, what are the literature review or what are the papers published in or scientific study, whatever they've done, they have done using this Bishop's modified method for giving a basic inspection of the slopes. So this method, that's why the reason for the another name for the Bishop modified method is police method. This is because just like an inspection, whether it takes place or not, just an inquiry, it takes place or not. For knowing this, the very simple method, we can use this method. And similarly, the rest of the methods were there, Jambul's method, and this method only forces were there, the vertical and horizontal forces was used, and there is no moment of inertia of loss was applied over here. And next one is Mostyn and Price method. In this, all the equilibrium proportions were considered, and even the horizontal vertical forces, moment of inertia, everything was considered. And similar for the Spencer's method. So here comes the problem 5. So what are the circular failures? So what type of failure surface was there, and what type of method to be adopted? So if the circular slip failure, then we go for ordinary method or as Bishop method. Rest of the what are the method, either is vertical or a planar failure, whatever failure has taken place, we can go for these 3 methods. And beside these 5 methods, there are a lot of other methods like Sharma method, which is of Indian who made this formula. And Sharma method, what are the advantage of Sharma method is it will consider seismic activities, means just like an seismic dynamic forces. So in Sharma method, Sharma consider the dynamic forces along with the horizontal forces, vertical forces, and moment of inertia. So here comes the topic, right? Now in this traditional method, what the problem actually is, all these what are the methods we have discussed till now, it consists of which it was evaluated based on the principle of statistics, means horizontal forces, vertical forces, moment of inertia. But the very important main cheese for the failure is what are neglected is strain and displacement. See, so if because and one more thing this was neglecting is internal deformation, because in the dams after forming the slopes, spoiled dams, so it takes some time for settling, right? So after what are the deformations taken after the settlement, and whether the brittle fracture is there or not, or developed or not. And other important, very important thing is progressive creep nature. What is this creep nature? So what this tells is, as the time goes on, the cohesion between these particles tends to get weaker. So once this cohesion gets weaker, it will be obviously it will fail. So generally, the term which will give this for this is strain softening, right? You might have had some analysis in the strain softening formula, because with the stress to strain, why do you do then the triaxial test? You go ahead, you draw a graph regarding the stress and strain. So on the top of the flare water, then the sample will fail. But even though the sample will fail, there are some strains will develop. So what is this is called as strain softening, right? And next comes the liquefaction of weaker soil layers. So as a spoil was there are a lot of materials, different kinds of materials, soil, shale, and sandstone, all these materials are there. So at that time goes on, what will happen? These material, the internal soil to soil will have some cohesion, but we doesn't know how this cohesion between the soil and the other material with the shale or sandstone. So at the times takes place, these calls what are the cohesion between them gets weaker. This known as liquefaction. So all this limitation was there because of the limit equilibrium methods. So to overcome these method, and And also another thing is, we have to know what are the area possible of getting the failure, which we call this shear strength reduction. There's a concept called shear strength reduction, which states that where the large volume of OB was there, right? So at which place it was going to fail, and what are the displacement of that failure, and how it is going to fail, what the amount of the OB they're going to roll down to this surface. So all these things should need to be evaluated. So for doing all this evaluation status, here comes the topics of numerical methods. Because due to this, in numerical method, what are the limitations in the limit equilibrium method is overcome in the numerical method. But what I mean to say, though the numerical methods were there, so here the concept of limit equilibrium was used in this methods also. Because ultimately we have to know the factor of safety. Until and unless we know the factor of safety, we doesn't decide whether the slope will take place or not. So here the concept, that's a limit equilibrium method, what was then, any one of the method to be taken and can limit analysis to be done here. So the finite element method, this is again I told you this shear reduction strength. So shear reduction is the available strength and strength at the failure. So this is a similar concept to the factor of safety. What the factor of safety deals with shear strength to shear stress, is the resting force to the driving force. So here also there's the same thing. What is the available strength at the time before failure, and what is the strength at the failure? So this ratio will give you a clear idea whether the failure will take place or not. So what actually different types of methods were there. So basically, this numerical methods were divided into two types. One is continuum method and another is discontinuum method. What is continuum method? Continuum method deals that all this material was homogeneous, right? So we treat this as homogeneous because as in the finite element method, as I told you, large bulk of OB will be considered, large mass was considered. So while considering large mass, obviously the what are the discontinuum was there, we treat it as an continuum model because there is no, we treat it as there's no continuum model. So okay, fine. Now continuum model we are doing. Then what is the difference between finite element method and finite difference method? So here comes the finite element method and finite difference method. Both actually the working principles was both of same, but what this difference comes is machine. See, as we everyone know, what is the, suppose we are at topography. The topography divided into very small particles, and how these small nodes or meshes were divided, your accuracy will be increasing. So now take an example of some surface. Right, we know that the surface obviously won't be of equal, some undulating surface will be there. So undulating surface was there, then how we will do this? When this go finite element method, the machine was done in the type of triangle. If you see this example over here, see, these was blocks are divided into triangles.
Vikram sir.
Sir. Hello.
Vikram sir.
Sir.
Please conclude in 5 minutes. The 8 o'clock is going.
Oh, sorry sir, lot more to be done, sir. Okay, sir. I will make sure that I'll go through very fastly.
5 minutes. So, 5 to 10 minutes.
Okay, sir. Thanks. So okay, this the basic concept. So I don't take much time. So but basic difference is this machine, right? Here is a triangle machine, and here comes the rectangle or square machine. Right. Then comes the finite difference method. So this is working behind this numerical method. So I don't want to discuss this, but we'll go to the next. So here comes the hybrid method. So why to use this hybrid methods actually? Because as I told you, when it comes to the large mass is consist of once you get this discontinuous, and at that place there won't be any discontinuous. So we have to cover both this discontinuous and non-discontinuous. So this hybrid method was developed. One of such method is the lattice method. So what this we will do is, you see this graph over here. All these nodes was there. This was springs. We call the springs. So these springs. So these springs.
Karan Kumar.
Okay. So this we divided these springs, and we'll apply some forces on this. So once the forces are greater than the shear force, the failure takes place along the joint plane. This is the discontinuity. The red color which are shown is discontinuity. You can see here, this is a discontinuity, and these are shear forces. This one is shear force, and these are vertical forces. Right. And this is a one-type method, and next method is material point method. So here there is no meshing at all. Right. In previous method, I told you the each and every part were divided into very mesh with very particle. But here in this method, there's no need of a mesh particle. So here what we'll take is where this is the last train, which is the last displacement there. We consider those zone as this metal point method, and we will evaluate these methods and will transfer. After getting this transformation, what we'll do, we'll move this to the continuum method, right? So these are the only two methods still now available right now, but not much studies has taken place. Most of the method we were using the finite element method itself, right? So here comes this advantages. I already discussed, so I won't go again. But here's a very important topic. What will go actually? How to decide whether it is go with 2D meters or 3D meters? So there's a few things to be not taken care of. Your principal structures which was there along the strike, it does not go within this 20 to 30 degrees. There's no need for going for 2D structures. And a meter of anisotropy does not strike within the 20 to 30 degrees. Then you have to go with this 3D models. And direction of principal is not parallel or not perpendicular slope, because if it is not parallel or not perpendicular, there's no need for going for 3D measure, because we can easily know by visualization, right? And distribution of geometric along the strike house of the slope and a geometry plane. Okay, these things was there. I'm going to skip this. And most what are the the general trend nowadays is going for 3D, but that's not necessary actually. See, some justification to be done why to go for 3D and why not to go for 3D, right? And next is another important topic is continuum and discontinuum methods. So as I told you, see, when it comes to the larger scale, we are neglecting this discontinuum. But when you see this a small, very small area, then comes with the discontinuum methods. So here comes to the experience of the geotechnical engineers, because they are the one who has to decide whether to go with discontinuum or the continuum method, because we decide based on the number of discontinuous in the span of 1 meter of area. So we take the 1 meter of area and we'll see whether number of discontinuous there. Based on those things, we'll decide whether to go for discontinuum or continuum methods. And another important thing to be remembered is when you go for continuum methods, all the failure criteria which is considered is Morse-Coulomb criteria. And when come to the discontinuum methods, the failure criteria to be considered is Hook and Brown criteria, because Hook and Brown criteria evaluates this discontinuous. But when it comes to the Morse-Coulomb criteria, no discontinuous was included in the analysis. This point should be remembered whether you go for a discontinuous or what are the failure criteria to be used in the software analysis. And here comes a few case study. So this is a section of the mine. We collected the samples, randomly 6 samples were collected, and we have brought this to the ISM, and we have prepared this sample, which consists of 2 meters of dug and a model size of 6 meter diameter and 10 meters the long. So this is why you are going for 6 meter diameter and 10 meter long, because this ISRM, International Standards for Rock Mechanics, had decided to be this height and the diameter should be of this thing, so that the sample will replicate the rock mass which was collected from the mines. So generally after preparing the rock mass, what are the parameters to be evaluated? So thus comes the unit weight. We already called the density, cohesion, internal friction, reverse pore water pressure. So how these all things will be measured? So first one is grain size analysis. So this is a video. The size was there, and we used different mesh size was there. So once you put the material, it will classify all those measures was there, right? So fine. This is a procedure for doing this. So I will quickly I'll move to the next other thing. So this a particular size was there here. So what type of a particle was there? Because this gives a basic idea, because this what are the type of soil, geometry of the soil. This is very important in analyzing the factor safety. And next comes the compaction test. What is the right way to do compaction test? The compaction test is used to measure dry density and moisture. So these are you see this is an example. I want to go more further. Just an image I was there. So see this there's a model was there. I collected samples from the mines and entered in this, and as compactor was taking place, and we are cooked in the dry oven, so that we collect the weight before this preparation sample, and then after drying out the sample, we collect the weight. Then we come to know what the moisture amount was there in the sample. So this is an parameters. Then next one is tag test. This is a known test. I don't want to discuss much about this, but from this we get the diameter, L by D ratio, all those things. And this is the software Rock Lab software, which was used for this analysis. So using this Morse-Coulomb analysis, what I got is for all the 6 parameters, we got the cohesion and friction angle. These are very important. After getting this cohesion and friction angle, we use the Morse-Coulomb criteria. From this Morse-Coulomb criteria, we get the shear strength. So once you get the shear strength, we already know the shear stress. So by implementing the factor of safety, if there was one, then the slope is stable. If it is below, that's a no common factor. So there are software in generated images. So section Y, fine. I'm not going to discuss about this. So these are very 6 profiles out there. The factor of safety was always above the 1, so there's no failure was there. So very next important topic, fine. Once you have got to the sample and you've done your established tables, so now comes to how to monitor these tables. So this is another case study I collected from the mine. So what generally do is, in that mine, they were using total station. So staffing was done and service station was there. And then after the better points were there. Then after this, the installation of the prism was taken place, and then after the prism was total station was installed at the high wall, and with the OB, there is a reflector points was installed at the various places. And once this prism sends the signals and the reflector hits back, and this whatever will collect the data, and they'll come to know what are the height of the, what are the reduced level of that point. And similarly, it will continually rotation will takes place, and continue 24/7 monitoring will be takes place. But what are the problem for this? What are the limitation has for this? So one of the limitation is this monitor takes at the particular points itself. It needs to be establish a reflector on the slope. Until unless you place the reflector, the data won't get for us. And the weathering conditions very important. So if you see here, you can see the figure here. There's a mist conditions over there here. So once you have the mist condition, the total station will drags and we are going to get accurate results from this. So these are the data which are collected from this prism. So all the problems was there, the external conditions, the heavy rainfall, the total station unable to work, and misty conditions. These are the limitations of these external conditions. So once you got it, now fine. What are the techniques as per available for overcoming the limitation which was had with the total station? So these are the various slope mountain textures. One is the visual, one physical visualization. These are highly impossible. Next comes the investigation instrument, photogeometric, GPS, satellite images, survey-based techniques. So survey-based techniques already I discussed here. So these are the various other techniques. This is the extensometer. You have seen the figure. So what this extensometer do is, this will find out what the elongation of the cement. Suppose the slope was there. Is there any elongation, whether in the displacement over there in the road? This will give us an idea. And this comes the piezometer. These are used to measure the water column in the mines. So what are the water column, how much it has increased or decreased, what is the state of the water column. By this you can get an idea whether to implement a drainage or not. So whether to remove the water column or not. This gives a basic idea. And let's tell very important two technologies till now available is INSAR. INSAR is for interferometric synthetic apparatus radar, and LIDAR is for light detection and drenching. So both these two both works on the principle of radar. They send the radar, and there's a OB was there. It reflects back. So once you get reflect back, it will collect the data and give the satellite image. Right. So INSAR mostly works on using the satellite images, and LIDAR mostly uses the laser. The laser turns and it gives an identification what was happening there. Right. So these two are used for the mass, very bulk mass, where there's a large volume of mass was there, where the movement of the mass taking place or not. This will be gives a basic idea. And here comes there are few limitation of this. INSAR is a very costly equipment actually. Though here comes a cost. This LIDAR is a very less cost, but effectiveness, the precision, very the precision talks about. INSAR will give a very minute details about this. But when it comes to the LIDAR, it will become fails when compared with the INSAR. But when it comes to cost, LIDAR will provide a cost efficient. So most of the mines are preferring for this LIDAR technology, right? So this is now. I think someone asked the question in the comment section where there is a guidelines for dump slope there. So these are few guidelines. I cannot say this are guidelines because see, if previous panelists told that even though the internal angular friction or this was there about 36 degrees, though it was in the 36 degrees, the spoil was failed. So what might be the reason? So based on the dealings or the guidelines, as per my knowledge or subject to the correction, what they have done is they are using the experience and the thumb rules was there. So these are those thumb rules. But this won't what to say always works on all types of rocks, because the geometry keeps on changing, and as I told you that the time being creep nature plays a vital role in failure of the dumps. So scientific study has to be conducted, a parametric study, that's what I discussed with the other panelists. So all those studies to be conducted. So what are the minimum technologies available as per now? So this is very few million. This is a rock fill trench. So OB was there. You can see the images. All the blasted wasted rock was there that are filled with this. This is friction piles. Another very important on this friction piles. As I said, the piles were digging into the underground, so that it get an capacity to block this failure of the OP. And this is another important factor, retaining walls. So these are used for actually the borehole was digged into the surface. the retaining was mostly used where there is the water, right? If the water was there, or the hillside was there, some water retaining there, whatever, all the water or aquifer, what was there, the water comes into this retaining walls, and on these retaining walls, you can remove this water, right? So next one is gabion walls. So generally what is a filled with wire will be there, and this wire was filled with all the mesh, wooden mesh, or whatever the available asynthetic what was there is filled with this. So this provides an stability to the spoil dam. And very important one is geogrid. This one very grid was developed. Once the geogrid was there, it was constructed along the spoil. And next one is sheath piling, and this is another type of stabilization method technique. So sheath piles were generated, and it was constructed in the floor of the OP. And these are very two important. We generally you will see in the hilly areas. These are roof wall system. See, roof wall concept, you all know the roof wall concept. The loose material has to be attached with the hot rock. It was there in the through this shear strengths. Right, roof walls will attach both these soft and hot rocks. The next comes this shortcut. So shortcut is another technique where the holes are made and is injected with this motor or concrete primarily at high velocities, and then after meshing will conducted such that the stability of the slopes will be increased. And another one is the biotechnical slope separations. This is another technique where we can see the vegetation was stable, where plants was this is common. You will see where all slopes were there. The plants roots which was there, it holds the loose material of the spoils. And dynamic compaction. This is nowadays we are using this and OBs. So what we'll do is generally the either dragline or whatever the available machine was there, we will use this weight loads from the we drop over this, that will creates a compaction in the OP. And if you use the better, we can use the dozer for dosing materials and all those things, right? And
Yes, sir,
the
please conclude.
yes, sir, yes, sir. So this is a drainage system. So this is soil fan. What are different types of explained? So it comes a conclusion. So what I mean to say is completely. So previous panelists had told that though yes, scientific studies are conducted, the failure are taking place. So here the lack of understanding the what type of failure mechanism to be implemented. So subject to the correction, the previous panelist has told that there's no much difference between the Mohs-Coulomb criteria and Hook and Rom criteria. So sorry to say this, but there is a variation between these two, because Mohs-Coulomb criteria rarely they want only for homogeneous material and no discontinuous was included. But when it comes to the Hook and Rom criteria, they include the discontinuous and non-homogeneous isotopic, non-isotopic natures. So here the lack of understanding what type of failure mechanism to be implemented and what type of limit of equilibrium methods to implement, thus plays a vital role in assessing the exact nature of this OP. So by this I'll conclude. Hope in a hurry I completed, but whatever it might be. So thank you all for having some patience and listening to me, and thank you for Karnakar sir, Jairam sir for giving an opportunity to express my share my knowledge on this topic. Thank you one and all.
Thank you very much, Vikram. Excellent informative, highly informative information. Your excellent PPT's presentation, excellent. Sir, JM sir unnara?
Hello.
Sir.
Hello.
Sir, please give the remarks, sir. Vikram sir is concluded. Please give the remarks.
Vikram is a research scholar. He nicely given the presentation. So congratulations.
Thank you.
So his research work nicely doing in ISM Dhanbad.
Yes.
In the presentation dealt different topics: introduction, factors affecting slope stability, and slope failure mechanism, traditional methods for slope stability, numerical modeling for slope stability, modern technology for slope stability analysis, case studies nicely as presented, mitigative measures, and conclusions. So he has given various open cast introduction. More than 90% of the colleagues from OC, and various problems in coal and OB extraction, and also benches making. More so in OB benches, there is a problem of social problems and environmental issues and different accidents. He has shown different mines, and nicely he has narrated about the slope failures and also various issues. And his research work has been
narrated very nicely. And due to shortage of time, he could not present properly. Very congratulations and
Thank you, sir.
all the best, Mr. Vikram.
Thank you, sir. Thank you,
So,
sir.
very nice presented paper, and I think we can conclude with these remarks. Thank you.
So, thank you, sir. Thank you very
Okay,
much, sir. Really, contribution of GM sir, great sir. You are given an excellent remark, and also panelists given a highly informative input. Most of them is questions and answers is asking in the text. Our time is limited. Next time we are inviting the physically Vikram sir to the Telangana state with cooperation of the Honorable Chairman Sir G.S. Janakiraman. Sir, Srikanth sir is the line. P. Srikanth, Assistant Professor KU. If you have, please give the vote of thanks. So I'm concluding, sir. I'm giving the vote of thanks. First of all, I am very thankful to the headquarters. They're giving the approval for the explained topic. And whenever the proposal given to the our director of DGMS, I. Sachinand sir, Dr. I. Sachinand accepted, and also Vikram sir also accepted. And also they're giving the valuable and highly information. More than 56 participants, most of them final students are there, and industry peoples are there. Some of the Australian peoples also participated. We're very thankful to the both of them. And also moderators are also GM sir, sir with late time also, he was extended cooperation to given the remarks for the patiently noted all the things. Thank you very much, sir. Thanks to Vandal sir, my team members also, all members of our Institute of Engineers Kottaguda Unit Committee members. I thanks to everyone to accepting this approval and more than giving the support to me, myself and Janakiraman sir. And also I thanks to the backbone of the Sri Venkatramaya Garu. With his only we are started excellently first webinar in our period. In future also, this is giving us to a motivated to be conducting in physically as well as a number of webinars in a different divisions, sir. Not only mining, it's also different divisions. Upcoming event is related to solar. I hope that is also continue. Sir, now I am adding national anthem. So I please all the attend. Thank you very much, sir. Thank you.
Thank you very much.
Thank you, everyone, sir. We are closing the webinar today.
Yes,
sir. We are closing the webinar today, sir.
Yeah,
thank you for
sir.
hosting.
Thank you, sir.
Thank you very much, sir. Thank you.